So given an object, like let's imagine you have like a plate and you want to find the center of mass. So that means that if I put like like a little needle or some sort of anchor, the plate will be perfectly balanced on that edge because that'll be the center of mass. So finding that special point that balances the object is what center of mass is. And of course, the objects can vary and you have different densities, you can have different shapes. So the center of mass will be a different place. It is not always right at the center of the object. It could be, it really depends. So let's get into the formulas and the theory. So moments. Center of mass. And centroids. Okay. So let's start off with something simple. Of course, I'm assuming you guys know the basics of force equal ma, right? Where that's equal to mass times acceleration. Moment is basically m times x. Right, so where x is the length of the moment arm, m is the mass. Okay, so think like a seesaw. That'd be the length of the arm would be the distance from the center of the seesaw to the seat, right? So yeah, something like this, I guess. Right. So you have one mass over here. We'll call that mass 2, and mass 1's over here. So the x distance is this. This is like one x1, one arm distance, and another x2 distance. Okay. And this little chunk right here is the moment arm. Okay, so moment about the origin we will call m, capital M sub 0. This is found by finding the sums of each moment arm times their distance, all the way till the final one. Okay, so basically adding up all these arms times their mass, right? So this x2 times that mass, this x1 times that mass, adding them up will give you the moment about the origin. So that's when the integrals are going to come in. You're going to find the sum of a bunch of these little rectangles and find the moment. That's what we're going to do in a little bit. So if m sub 0 is equal to 0, then the system is said to be in equilibrium. Okay. For a system that is not in equilibrium, One moment. Give me a moment. I'm sorry. I have family over and they're very distracting. Give me 1 second. General idea here. So for a system that is not in equilibrium, the center of mass is defined as x bar, as the point x bar, at which the moment arm also called the fulcrum could be relocated to attain equilibrium. Okay. Ready? So the moment and center of mass. So now let's get, so this is for the general theory here, but now let's get to a one-dimensional problem and then a two-dimensional. So moment and center of mass for a one-dimensional problem.
What is that word in parentheses after the arm?
Fulcrum.
Fulcrum.
Yeah. Just another word for the moment arm. Okay. Okay, so where is my formula? So let the point masses M1, M2, Mn be located at x1, x2, all the way till xn, respectively. So number one, the moment about the origin is capital M0 equal to, you multiply these point masses times their location, x1, respectively. So we're going to get a sum of M1 x1 plus M2 x2 all the way till Mn xn. Number 2, the center of mass is x bar equal to M0 over M, where lowercase m is the total mass. That is to say, M1 plus M2 plus M3, all the way till Mn. So if you have a simple problem like, I don't think I have space here, but I think I do. Let's see. Find the center of mass of this linear system. So if you know all these points are on the line, like maybe like a seesaw or something, just gonna write down the masses and the locations on the chord on the number line. So if you have all the masses, all you got to find the little m, all you got to do is add them up, right? Because they're all little points, point masses. All right, so I'll give you time to write for a second. I know there's a lot of details here before we get into the big problems. Okay, so to find the center of mass in a 2D, in a 1D dimensional or one-dimensional problem, all you got to do is divide the m naught by m. So m naught is easy to find, you just add them up. So that'll just be 10 plus 15 plus 5 plus 10, right? Which is what, 10, 15, 5, 10. It's 30, right?
You scroll up the notebook.
What's up?
You scroll up the book, the notebook.
Oh, yeah, let me move this a little bit.
There you go. Thank you.
It's 40, by the way.
Now to find the m naught, all we have to do is multiply each of these masses times their x1s, x2s, etc. So you're going to take 10 times -5 plus 15 times 0 plus 5 times 4 plus 10 times 7. Kind of out of space here. Let me write this on another page. Stop being weird. You guys got the other stuff though? I'm gonna rewrite that question. Or should I turn back?
Just continue, I guess.
There's no rush. Do you need the? Any stuff
Uh,
missing? I'm gonna rewrite this part, so you don't have to write that.
Yeah, go ahead.
Okay. I'm gonna start the problem now. Find the center of mass for the linear system. So they gave us the system here, all the masses and their respective distances. So we had 10, -5, and 15, 0. We had 5 and 4. Let's see, what was the other one?
And 7.
It was 10-7.
And 7? Oh, yeah. Okay. So these are the formula, right? Little m is just the sum of all these masses. Capital M0 is the product of each one. What is this total? $20, 70, 40, right? That right? So the center of mass, which we denote as X bar because it's the on an X axis, right? we're not finding an X and Y equilibrium point.
M would be 40, not 30.
40? Oh, yeah, thank you. So it'd be 40 over 40. So center of mass for this guy is 1. Now let's do something harder. Let's see here. So if you had if you had points instead of just x distances, you would have to find. I'm going to go to a harder problem. So if you see one that has, that's instead of just an x, you have a y, you'll have to find mx and my instead of just m0. So you'll have 10 times -5, 15 times 0, right? All these for the x values, and you have another one for the y values. So yeah, you'll have a x bar and a y bar. So I'm going to move on to two-dimensional where we have to use integrals. That's where we're going. Moments and center of mass of a planar lamina. So basically that's just a thin, this is a thin flat plate. Of material of constant density. So it's the same density all the way around on the object. Okay. Where is that formula? Well, I guess we should write this first. Since we'll call it density P. Let f of f and g be continuous functions such that f of x is greater than or equal to g of x on an interval AB. And consider the planar lamina of uniform density P bounded by the graphs of y equal to f of x y equal to g of x. And let's say that x is between some a and b. All right, so now we can write our formulas. The moments about the x and y axes are, all right, so number one, mx is equal to p times the integral from a to b of f of x plus g of x over 2 times f of x minus g of x dx. So the moment about the x is going to be this guy. The moment about the y is going to be this. To be x times f of x minus g of x. That's number one. So that give me the moments. Now the formula for the center, it's going to be something else. Well, wait a second and write the rest of the next page. Just a moment. So to the center of mass, which we'll call x bar, comma, y bar. So that's a location of the center of mass. So this is given by x bar equal to my over m, lowercase m, and y bar is equal to mx over m, where little m is equal to p times the integral from a to b of f of x minus g of x times dx. This is the mass of the lamina. Okay. Do you remember those little birds you used to sell? You'd put them on the tip of your finger and like a little toy would balance perfectly from the beak. Right, that perfect balance, that's the center of mass we're looking for on the object. So we're going to have functions we'll create like kind of like we did the area, remember area between curves. So we're gonna have a little boundary, and we're gonna try to figure out what is the center of mass for that boundary, that object that we created, that we create with functions. Okay, that's what we're gonna do. So we're gonna have to find the total mass of the object, and then the moment about the y and the moment about the x divided by the total mass, and we'll have the location of the center of mass for two-dimensional problems. Okay, so this is assuming that the object is completely flat with uniform density. Okay. So let's start. First legit example. Find the center of mass for the lamina of uniform density P bounded by the graphs of y equal to square root of x plus 2 and y equal to 1/5 x plus 2. So let's graph this on Desmos and see what it looks like. So we got well, the square root, that one's easy to, we know what that looks like, right? So the bounded region they create is right here. So there's a little section. The picture this is some piece of some object, some flat object. I want to know what is the center? Where can I find perfect balance if I had a needle and I put this piece on top of it? So we need to use the integrals and the formulas to find them. So we need the x bar location and the y bar location. That'll give us the exact spot. Okay. So just gonna sketch this over here from the picture. Picture sucks, but whatever. Okay, so we know that the intersections are at 0 and 25 thanks to the graph. Now, let's find the total mass first. So let's find little m. We said little m is the integral. Let's go from 0 to 25 of f minus g. So which one is the f?
It's square root of x plus 2.
Yeah, square root of x plus 2, that's right. So that'll be f minus the g. solve this dx. Okay, so that's times p though, right? We don't know what the hell p is. So m will equal p times that integral. Okay, so be root x plus 2 minus 1/5 x minus 2. So those 2's are gone. So the integral will be add 1 to the root. So that will be what? 2/3 x 3/2, right?
Mhm.
Squared minus 1/10 x squared from 0 to 25. So p times square root of 25 is 5. 5 cubed is 125. So 2/3 times 125 minus, what's 25 squared? I don't know what that is.
It's 25.
625.
Thanks. So there's our answer. That's about 125 over 6p. Once you do the math, that'll reduce, yeah. Okay. All right, so we got the total mass. It's this times the density, p. We don't know what the hell p is. It was not given. But when it comes to finding the center, it's not going to matter because the p's will cancel. If you remember the formula, x bar will be divided, have the moment of y divided by m. So that would be canceled. So we need to find capital My and Mx. So I don't think I have space here for that. Okay, so we're gonna need this guy. Yeah, let's go ahead and do it on the next page. So what I'm gonna do is use this formula to find, we need these guys right at this moment, capital My and Mx. So we need the integrals to find each of those, and then we'll divide by this m that we just found. Okay, that's where we're headed. So that'll give me the location of the center. Well, I'll wait a bit if you're still looking at this.
Okay, I'm ready.
All right, so let's pull out the formulas. Where would I write them? There they are. So we need to find Mx, which is the integral p times integral a to b of f of x plus g of x over 2 times f of x minus g of x dx. So that will be p times the integral from 0 to 25 of f plus some nonsense. What the hell was f? Root x plus 2, right? G was 1/5 x
Well,
plus 2, or what was it?
let's do
Okay. Times the subtraction, which would be root x minus 1/5 x, right? Okay. All right. Combine, we're going to multiply all this nonsense, combine the like terms first before we integrate. This will be square root x plus 1/5 x plus 4 times root x minus 1/5 x dx. Oh man, I gotta multiply all that garbage. That sucks. Life sucks. Okay. All right. Here we go. Root x times that guy is going to be x, right? Root x times this one will be negative 1/5 x to the 3/2. Okay, now the next one. 1/5 x times that guy will be plus 1/5 x to the 3/2. Cool, that'll cancel. 1/5 x times this will be a negative 1/25 x squared for root x, and then minus 4/5 x dx. All right, so I did all the multiplication. Let's see what cancels. There's an x and a 4/5 x. So that'll be negative, no, it'll be positive. A 1/5 x. These are gone. Plus 4 root x minus 1/25 x squared dx. Excuse me. Okay. Now it's time to integrate, finally. So this will equal p times 1/10 x squared plus, that would be 3/2, so divide that. Be 8/3 x to the 3/2 minus 1/75 x cubed from 0 to 25. All right. All right, sorry, I know there's a lot of algebra here. You guys okay with these little steps? I don't want to skip so much, but there's a lot of, so many of them, you know. That it's hard not to go a little faster. Okay, so at this point, we're just plug in the numbers, right? It's a fundamental theorem of calculus. Let me see if I have the number written down somewhere. Biscuits. Did you notice what I forgot?
The 2.
Yeah, I forgot the 2. So to make, so I don't have to erase all this, I'm going to do this. Okay. Okay. Now we're not wrong. All right. So plugging all the numbers, you'll end up getting, I'm just going to skip this part because this is taking way too long for one question. It'll be 375/4p. So there is mx. Any questions on m, the moments about x? Right, we're just using a formula, we're just integrating, we're not doing anything crazy. Just gotta be careful with your algebra and your integration. Okay. Okay. The moment about the y is a little easier. So my is equal to p times integral from 0 to 25 of just f minus g, right? Or x times that, sorry. Yeah. Actually, let me double check. Where is it? Yeah, f minus g. So ours will be minus x to the 1/2 plus 2 minus where's g? That was 1/5 x, right? Plus 2. So that'll give us okay. So at this point, just integrate and we're good. That'll be x squared over 2 minus 1/15 x cubed p from 0 to 25. So that will be, let's see, 625 over 3 p. Okay. So finally we get a moment of x, moment of y. We've got the total mass. Now all we have to do is divide. And we get x bar and y bar. And we're done. So it's more tedious than difficult, in my opinion. Because at this point, the integrals are stuff you've done before. They're like basic ones. It's just using the formulas and then setting it up correctly. That's it. So x bar is equal to the moment of y over total mass, which is 625 p over 3 divided by, I already forgot what little m was. P's will cancel. This will reduce to 10. There's x bar. Y bar will be mx, moment of x over total mass equals to mx was 375 p.
Can you scroll up the notebook?
Yeah, thanks. 375 p over 4 divided by total mass, which is 125 p over 6. So this will be 9/2. So the center of mass is going to be 10 comma 9 halves. So that's the location where that object that we graphed at the very beginning will have a perfect balance. Any questions about that? You see what we're doing, right? All we're doing is calculating my, mx, and divided by total mass. That's all we're really doing. It's just that each one is technically an integral. There's 3 integrals we had to do.
So we have to identify those points into the graph, the 10 and 9.2, on 9/2.
Yeah, that's technically what it is. Let's see here. I put the point in there just to see where it's at. 10, 9 halves. Oops, there's parentheses down there. That little green dot is the perfect balance for that object. So if it was a flat piece of paper or plastic or whatever, and it's the same density, if I put a little toothpick right there, it'll be perfectly balanced.
Okay. Now, let's say you don't know, how do you find the density of an object? Like, is that a totally different subject? Right?
Yeah, I mean, density is based on material, and depending on what type of material we're talking about, the shape. Yeah, I mean, you can calculate density, like in like higher level classes, or they'll probably give you, they'll tell you what the material is, and you'll have to look it up in a book and say, okay, what is the density of this?
Oh, I see.
That's probably usually what engineers do, but given some other information, like in chemistry, you can calculate density of different things. It's not a big deal. But for these problems, it's easier to assume it's uniform, because once we assume it's not, then it's a really strange object, number one. Like, why would you have it all? Why wouldn't it be? It's number one. But number two, once it starts getting to like 3D objects, these equations get a lot more complicated. Yeah, I think that's the only example I had, actually. Let's see here. They take forever, but I at least want to mention some ideas before we stop. Let me show you some of the homework. See number 4. Oh, let's look at the easy one first. Yeah, I guess number four is a little harder than the first one we did. So remember how we found the little m, you just add them all up, right? Who cares? That's the total mass. Mx, you'll have to do 5 times 2, 1 times -3, 3 times 1, and add them up. That'll be the moment of x. And then to find the moment of y, you'll do 5 times 2, 1 times 1, 3 times -6. So you'll have, that's how you get the 10/9 and the -7/9 by just adding those up. Same thing here. It's not difficult. Just multiply the corresponding masses times the x's for the x bar, and the mass times the y's for the y bar. That's all we're gonna do. Let's see here. This one is similar to what we did, except this one's a little easier. Let's see what the graph looks like. y equals 1/8 x. Equals 0. X equals 8. So this is the other one. This is like a perfect triangle, so this one will be a lot easier. Right? So you integrate from 0 to 8, and you'll find the center of this triangle. So you'll find the total mass, and then divide that into the moment of x and moment of y. So first you do this integral, then you do this one, and you divide each one by little m. Anyway, you guys have any questions on the main idea? Does the concept make sense? What we're doing?
Yeah, it'll take practice though.
Is it not too bad, or do you feel it's difficult? I don't know. Trying to get a feel for it.
Oh, no, this subject to me right now, it's above my head. To be honest.
Gotcha.
Have to process it.
But you see what we're doing, right? Like the ball.
Yeah.
Yeah, of course.
Okay. You want to do number 6, or does this one make sense?
Number 6 is easier because g of x is 0, right?
Yeah, I think it's a little easier because of the shape, and the integrals would be easy. So when you're doing f minus g, this is going to be super easy because it's a 0. Exactly.
Yeah, that's what I was saying.
Or I did a hard one. I don't know why, but the ones in the homework are a little bit easier, at least up until 6. I think 7, 8. 7 and 8 are more like the one I did. See how number 8 looks like the one I did?
Mm-hmm.
So this one will be the hard one. The easy ones, when I say easy, I mean easier than what we just did. 1 through 6 will be easy.
I mean,
So,
it'll take me less if you give me an object, now find the center just by, try to balance in it, then doing the math. So,
that's funny.
no, but yeah,
Trial and error.
correct.
That's funny. Yeah, I mean, I'm sure we can eyeball a lot of stuff, but if the object is huge or too heavy, it's probably
Yeah,
like,
Then it exact points, shoot.
yeah, this shit becomes important. Like when you want to find like the fulcrum of a wing, airplane wing or something. You want to be exact. You don't want to be guessing. You know.
Okay.
Yeah, let's do 6 real quick. That's fine. I think 6 compared to the last one. So we got, so example 3, problem 6. Y is equal to 1/8 x. Y equals 0, x equals 8. So we had that shape that I graphed earlier.
Your record?
What's up?
Your record is okay.
Oh, yeah, sorry, yeah. Just wanted to switch real quick. Okay, so we had a shape like this, right? So this is the line, 1/8 x. So the integral, so first let's find little m, right? What was the formula for little m?
It was little m
F of X minus G of X.
X.
That's it, right? F minus G?
Yes.
Okay, so which one's F?
1/8 X.
Yeah. So 1/8 x minus 0 dx. So the integral will be 1/16 x squared from 0 to 8, which is 64/16 minus 0, which is, what is that? 4?
Yeah, 4.
Okay, so now mx. That should be p, right, technically?
Yeah.
Mx, what's the formula for mx? This is the harder one.
F of X plus G of X.
So f of x over 2 or no?
Yeah, over 2.
So I'm gonna put the 2 over here, p over 2.
And then it's times F of X minus G of X.
Okay. So that will be p over 2, integral from 0 to 8 of 1/64 x squared dx. So integrate this guy. What's 3 times 64?
192.
Okay, so this would be x cubed over 192. Okay, plug in the 8. So that will be from 0 to 8. So that will be 8 cubed.
512.
Okay. That's going to reduce, right? What does that reduce to?
Two oh six over, no, 220, 232. Yeah. Actually,
Oh, 16 goes into both, right? So that's going to be what, 4? No. Uh,
32 divided by 24 is 1.33.
8 goes into 24, right? Yeah, 4/3 p. So this is mx. This is what they got on the homework. My, what is the formula for my?
X times F of X minus G of X.
So integral from 0 to 8 of f of x minus g of x. Oh, times x, right?
Yeah, all that times X.
P. Okay. So that will be
oh,
x cubed over 24 4, right? From P 0 to 8. And we said 8 cubed was 512, right?
Erika. ¿Qué pasó?
Looks like 8. So this will reduce to 64p thirds. Okay. So now we just find x bar. Divide these guys. So my over m will give us 64p over 3 divided by little m, which is 4p. So that will be 16 thirds. It's too close, probably. This guy will be 4 thirds p divided by 4p, which is 1/3. And there we go. That wasn't as bad as the other one, right? So that's what they got for mx, my, and this nonsense. Any questions on number 6? So I did one hard one and one easy one. I'm hoping you won't struggle as much with the homework.